Hello, this is Tracy. Welcome back, Math 135. We are still in Chapter 7, the central limit theorem, and we are going to do a second example. So here we have a prototype automotive tire has a design life of 38,500 miles with a standard deviation of 2,500 miles. 5 such tires are manufactured and tested on the assumption that the actual, not just the design, mean and standard deviation are 38,500 miles and 2,500 miles, find the probability that the sample mean will be less than 36,000 miles. Assume the distribution of lifetimes of such tires is normal. Otherwise, a sample size of n equals 5 is too small. So that's our first question. If we take 5 of these tires, run them until they die, find the lifetime of each of the 5, and then average them, what's the probability that the sample mean is going to be less than 3,600 miles? And then the next question is, what sample mean would be unusually low? What value divides the lowest 5% of these sample means from the remaining 95% of sample means? As you recall, we have two normal distributions we'll be looking at here. The first normal distribution is the population distribution, the distribution of lifetimes for all of these tires out there. And we know the mean of that population distribution is 38,500 and the standard deviation is 2,500 miles. If we pick a tire at random, just one, that is the distribution we would use. The sampling distribution of the sample means that is the distribution we are going to use when we repeatedly take samples of 5 tires, find the average lifetime for those 5 tires, and then plot a frequency distribution. We will get an approximately normal distribution that has the same mean as the tires, 38,500, but a much smaller standard deviation. As we can see in the curves, the population has a short, stubby population distribution, but the sampling distribution of the sample means is a normal distribution that's much taller and skinnier. So going on to that first question, we want to know the probability that X bar, the mean of our 5 tires, is less than or equal to 36,000. And we're going to do this on our calculator. We're going to use that normal CDF function. We go to second vars for our distributions and we scroll down to the normal CDF. And we want to find the area under the curve for this normal distribution to the left of 36,000 miles. So you can see that area shaded in on our normal distribution. So normal CDF, the lowest value we type in is something ridiculously low, so negative 10 to the 99. If you want to, you can also use 0 because a tire can't have less than 0 miles on it before it dies. It really doesn't matter. Your answers aren't going to be that different from each other. So our lower bound to the left forever, or 0, so 0 or negative 10 to the 99. Our upper bound, that would be the 36,000 miles. That's the longest average lifespan that we want to consider. And then our mean and standard distribution, 38,500. And then the standard deviation for this sampling distribution is that 2,500, the standard deviation of the population, divided by the square root of 5, the sample size. And you can type it into your calculator like that. That's going to give you a more accurate result than calculating 2,500 divided by the square root of 5 and then typing in a decimal approximation. So when we put that in our calculator, we get about 0.0127. About 1.27% of the area is in that little shaded chunk to the left of 36,000 miles. So that means that the probability that the mean lifetime of 5 sample tires If we assume that the population mean and standard deviation given to us are both correct, is about 1.27%. So what that tells us is that we either got an unusual sample, pretty unusual, sample that only shows up just over 1 out of 100 times. So we either got an unusual sample or the mean and or the standard deviation given to us are incorrect. Either the mean or the standard deviation or both that are given to us are incorrect. So then the next type of question we could ask, what mean for these 5 sample tires is unusually low? In other words, what value divides the lowest 5% of means from the remaining 95% of means? That's shown by the area here where we say we want to know what average lifespan for these tires, what average lifespan divides the 5% of the lowest averages from the rest. That's asking us to find the 5th percentile. And our calculator can do this. We would use the inverse normal function, inv-norm. So we go to second vars into our distributions, and we scroll down till we get inv-norm, I-N-V-N-O-R-M. And the syntax for entering that to the calculator is we type in the area to the left, or that's the same as the percentile converted to a decimal. So we type in the percentile or the area to the left of the value we're looking for, comma, mean, comma, standard deviation. So here we have what we put into our calculator, inverse normal, 0.05 for the 5th percentile, the value that bounds the lower 5% from the upper 95%, 38,500, that's the mean of the sampling distribution of the means, and again, 2,500 divided by the square root of 5, the standard deviation for the sampling distribution of the means. Type that in and we get about 36,700. So that means the lowest mean lifetime for 5 tires that would not be considered unusual is about 36,700 miles. All right, well, that was another example. Again, let me know if you have any questions, and we will end this example.